Greetings. Welcome to our lecture series on structural mechanics 2. In this series, we'll be discussing about moving loads and construction of influence line diagram. In structural mechanics, we come across various types of loading such as dead loads, live loads, wind loads, seismic loads, and impact loads, which are acting in the form of point load, uniformly distributed load, or uniformly varying load, and they may have action like push or pull. All this mechanics which we have learned was related to the stationary position of the loads acting on the structural member. When this load traverses from one end to the another end along the length of a structural member, we term them as a rolling load. The real life example of rolling loads are a train moving over a railway track or a vehicle moving on a bridge or a roads. Let us assume a simply supported beam representing the deck slab where a truck is traversing from one end to the another end. The loads from the truck and self-weight of the truck is transferred to the deck slab through wheels. The wheels has a smaller contact area, that's why we can idealize the wheel load as a point loads acting at a fixed distance, which is the fixed wheel base, forming a train of loading. While traversing, this train of loading will occupy a different position along the length of the structural member, and they may reproduce the different envelopes for response parameters. The construction of such envelopes representing different response parameter is termed as a construction of influence line diagram, and the analysis of such a loading system will term as a rolling load analysis. In case of rolling load analysis, we will be dealing primarily with the 4 predefined cases, which includes single point load rolling over the structural element. The interest will lie to know various response parameter like variation of reactions at the end for different position of the point load and variation of shear force and bending moment at various section with position of the rolling loads over the span of the structure. Second case will be dealing with a uniformly distributed rolling load. If the vehicle is having a closely spaced wheels, that can be idealized as a uniformly distributed load system, and this wheelbase is smaller than the span of the structure, means partial span of the structure will be covered. In that case, we can term that as UDL, shorter than the span. When the wheelbase is larger than the span of the structure, such as a long train is going to move over a short span bridge, then we can term that as a UDL, longer than the span of the structure. Similarly, if fixed wheel bases are there and system of wheels are there which are representing multiple loads, then we will call them as a train of loads. There may be dual wheels which are moving over the structure, or there may be multiple wheels which are moving over the structure. The interest lie here to find out the variation of response entities like reactive forces, shear forces, and bending moment at different positions occupied by the loading system along the span of the structure. To begin here with, let us begin with the concept of equivalent UDL. As we know, there are different forms of load which are going to act on the structure, like a series of point load is going to act. We can say system of point load is going to act on the structure, then uniformly distributed load and uniformly varying load. When it is supposed that response is to be ascertained with reference to series of point load, then it will become a tiresome job to find out responses under such a loading condition, as individual effect of the wheel loads point load has to be considered, and it will require some cumbersome exercise. So one may say that can it be possible to represent the point load system into a uniformly load system to have a convenience in finding out the responses of the given loading system? There may be affirmative answer, yes, this can be done with a surety that the effects of this loading system will get unaltered. Means we are going to convert the point load system into a equivalent UDL system, taking care that there will be no alteration in the action of the load system which is going to act on the structure, but it will help in convenience to find out the response parameters. So the answer can be written as a given system of point loads can be converted into a system of uniformly distributed load longer than the span, so that the shear force and bending moment at any section of the beam due to equivalent UDL is equal to that caused by the system of point loads. Let's have an example here, example conversion here with reference to a single point load converted into equivalent UDL. For that, what the surety we have? We should have no change in the effects which are produced by the loading system. So when let's consider this rolling point load is going to act at the mid span, then for this case the shear force diagram will be as shown in the figure, with maximum value of W by 2 at the ends. Whereas if we are interested toward the bending moment variation, the bending moment at the below the load will be WL by 4. Now we are in interest to convert these loads into equivalent UDL. For that case, we will say the UDL, the conversion will be in such a way that there is no alteration in the effects. So for this equivalent UDL, if we find out the shear force distribution, it will be W dash L by 2 linearly varying at the ends, and bending moment at the center will be equals to W dash L square by H. To find out the equivalent value, we have to equate the bending moments generated due to both conditions, like WL by 4 for point load is equals to W dash L square by H, from which after simplification we can find equivalent UDL W dash is equals to 2W by L, ensuring that there is no change in the effects. Similarly, if I want to find equivalent load, then we have to equate the shear forces in both the cases. So W by 2, the shear force in point load action, W dash by L into L by 2 for the case of UDL. If we equate, we get equivalent load, which is given by relation W by L. Now let us have a small numerical on this to have the understanding of the concept. The statement of numerical is a simply supported beam carrying a point load of 100 kN over a span of 2.5 meter. Convert it into equivalent UDL. So what the relation we have developed? Equivalent UDL can be written as 2W by capital L. So here 2 into 100 divided by span of the structure is 2.5, it yields to 80 kilonewton per meter. If suppose one is interested to know equivalent load, we can get this equivalent by the relation W by L, which equals to 100 divided by 2.5, that is 40 kilonewton. Hope you have understood the simple conversion here. Let's move towards the next concept related to absolute bending moment and shear force. We came across a statement maximum bending moment and maximum shear force, which we say that this is the maximum value of bending moment or the shear force at a particular location or for a given loading condition. But in the case of rolling loads, loads rolls from one part to the another part. At individual part, they are going to develop a response entity. Thereby, there will be a variation in the bending moments or shear force along the span. The maximum value which is obtained throughout this traverse is said to be absolute bending moment, which is different than the maximum bending moment. In case of maximum bending moment, we have predefined location and predefined loading condition. But here there is no such predefined position, and the combination of load will be different, and it is going to traverse along the length, and we are going to get multiple envelopes. From this multiple envelope we will choose the maximum value, and that maximum value of the responses will be said as the absolute value for that particular response. So if we code this in terms of statement, it can be stated that the greatest value of maximum bending moment calculated at various sections along the length of a span is called absolute maximum bending moment, and that too in terms of traversing load or rolling loads. To illustrate this concept, let us consider that when a train of load is moving along a span, we can calculate maximum bending moment at a defined section by placing average load on left hand side is equals to average load on right hand side. Likewise, at every section along the length, we can calculate one maximum bending moment. From this set of bending moments, if we pick up the greatest value, this is known as the absolute maximum bending moment. That is, no other bending moment is greater than these values. For example, the figure illustrated here, for a fixed position, I will get a fixed value of response sensitivity, and this value will be called as a maximum. But when it is going to traverse, we are ensuring that either there is a balancing of the load or there are the multiple responses developed, and the peak value of these responses will be termed as